work for Tencent Cloud. This is today's agenda. I will introduce the PV TLB Shootdown to scale high ratio over commits. The second one is Exitless IPI to scale large VMs. And the third one is to disable mwait hot or pause instructions vmexits to improve latency for the dedicated instance. All these features are upstreamed by me this year. Here is the background of the TLB Shootdown Preemption. When executing inside a virtual machine environment, OS-level synchronization primitives such as locking, TLB Shootdown, and RCU are faced with significant challenges due to the scheduling behavior of the underlying host scheduler. Operations that are ensured to last only a short amount of time on bare metal hardware are capable of taking considerably longer when running virtualized. A TLB is a catch of translation from memory virtual address to physical address. When a CPU changes virtual to physical mapping of an address, it needs to invalidate other CPUs still mapping in their respective caches. This process is called TLB Shootdown. Modern operating systems consider TLB Shootdown operations to be performance critical, and so optimize them to exhibit very low latency. The implementation of these operations is therefore architected to ensure that shootdowns can be completed with very low latencies through the use of IPI-based signal. Remote TLB flash does a basic wait, which is fine in bare metal scenario, but within the guest, the vCPU may have been preempted or blocked. In this scenario, the initiator CPU would end up basic wait for a long amount of time. It also consumes CPU unnecessarily to wake up the target of the shootdown. The time between the preemption and the rescheduling of a remote target vCPU is often orders of magnitude larger than the latency that the TLB Shootdown operations were designed for. This is the CDF of dedupe benchmark, the TLB Shootdown latency. We can observe 1 VM, which means it is not overcommit. 2 VM, it is the overcommit ratio is 2. We can observe the latency increase in several orders of magnitude. The PV TLB Shootdown does not wait for vCPUs that are sleeping. Instead, KVM will flash the TLB as soon as the vCPU starts running again. The improvement is clearly visible when the host is overcommitted. In this case, the PV TLB flash prevents printed vCPU from stealing precious execution time from the running ones. There are two cache translation information while EPT is in use. One is guest physical mapping. It is guest physical to host physical mapping. The other one is combined mapping. It is guest virtual to host physical mapping. Operations that are architecturally invalidate entries in the TLB, for example, through NVLPG instruction, will invalidate combined mapping while EPT is in use. There is a virtualization instructions, NVVPID. It also invalidates combined mapping while EPT is in use. So the effect between guest execute NVLPG instruction to invalidate TLB is the same as KVM use NVVPID to invalidate the TLB. Let's see the implementation details. I introduced a KVM vCPU preemptive flag. This flag is used to mark whether or not the vCPU is active or inactive. I use a shared memory between the shared memory is between the guest and host. The host record the flag, the vCPU preemptive flag when the vCPU is preempted on the host. The flag will be clear before the next entry of the vCPU. So through this flag, in the guest, we can determine whether or not the target vCPU is active or preempted. I add a flash TLB other hook to the PVMMU ops. It will call IPIs for the active vCPUs directly as before, but for the inactive vCPUs, it will record another flag, KVM vCPU flash TLB flag, which means the vCPU is preempted and we need do another TLB flash before the VM entry. KVM will just do the flash where MVV PID on the guest behalf the next time the vCPU is scheduled, if KVM vCPU flash TLB flag is set. So we do a delay TLB flash here because the at least as long as the vCPU is not a VM entry. Again, the vCPU will not consume the stale TLB mapping, so it is safe to flash the TLB by the hypervisor the next time the vCPU, before the next time the VM entry. I tested the performance on one Scalable server. It has 64 logical CPUs, and the VM is also 64 vCPUs. I will try one VM, which means it is not overcommitted. 2 VM, 3 VM. 3 VM, the overcommit ratio is 3, and the commit ratio is acceptable on the public cloud. The benchmark is eBusy. It is highly threaded and has a large in-memory working site. It will frequently allocate and deallocate memory, so a lot of TLB Shootdown. Here's the result. The blue histogram is the vanilla KVM. The orange one is with the PV TLB Shootdown. We can observe for 2M scenario, in each VM, the performance dropped by 49%. For 3 VM, in each VM, the eBusy score dropped by 65%. And after the patch, we can observe the obvious performance improvement. Even if for the non-overcommit case, 1 VM, we still can observe a little performance improvement because the host CPU is not absolutely isolated. As you know, the QEMU has IO thread, and there are also housekeeping processes which are running on the host. As long as there is preempted, we can get the benefit. The second feature is Exitless IPIs. APIC, which is short for Advanced Programmable Interrupt Controller. It has 2 modes. One is a legacy XAPIC mode. The other is extended XAPIC mode, which is also called X2 APIC mode. the X2 API mode is really common in recent Intel generation, so we just talk about X2 API mode now. The API, the OS will write the ICR register to send APIs. There are two stub modes to determine the API destination. One is cluster mode. The OS just need to write ICR register once, then the CPU hardware will help to broadcast the APIs in a subset of processors on the system bus. The subset of processor is the cluster here. It is max 16 logical CPUs per cluster. The other mode is physical mode, which means the OS need to write ICR register one by one. Currently, most cloud providers just support physical mode. The guest can just enter the physical mode. And several years ago, Red Hat guys post the interrupt remapping patches to the VLMMU in QEMU. Then we can enter the cluster mode, but most of cloud providers have not enabled this. Each rise to ICR actually, at the last presentation, we have already know, like Google, they have 160 vCPU VMs, which means if one vCPU broadcasts APIs to other 159 vCPUs, it will incur 159 vmexits. Yeah, but on bare metal, it is not we cannot obvious performance drop. But on virtualization, one VM is large. The vmexits are too many. This is the implementation. Currently, these features are merged to upstream. I will set the destination to a bitmap in the guest, then use a hypercall to send APIs to multi-vCPUs. The hypercall lets a guest send multicast APIs with at most 128 destinations per hypercall in 64-bit mode and 64 vCPUs per hypercall in 32-bit mode. The destinations are represented by a bitmap contained in the first two arguments of this hypercall. The bitmap will be scanned in KVM, then to send APIs to the target vCPUs. Let's see the performance evaluation. I use a scaling server, total 80 logical CPUs. And the VM is also 80 logical vCPUs. I use a API macro benchmark. We can observe the time to send the multicast API to other vCPUs. In X2 API physical mode, the performance can be great improvement. Even if in a cluster mode, we can still observe some benefit. The last one is to disable mwait or halt or pause vmexits to improve latency for a guest which has dedicated physical CPUs. Actually, 3 years ago, I pushed the adaptive hot pooling to upstream. It will not consume too much CPUs since the adaptive algorithm. But if you already can tolerate idle is equal to pool in the guest graph, which means you can observe 100% CPU occupation by a top command, then you can try this. Here, take a disable mwait as an example. To disable the mwait intercept, we can give guest a limited power management capability. A guest can put a physical CPU into a power-saving stage. Let's see the Unix bench. We can observe the improvement. I do another testing to compare disable mwait and idle is equal to pull. Here, I test on a desktop which has 8 logical CPUs. Then 2 VM, each VM is 4 vCPUs. There are 2 test cases. The difference is test case 1, both idle is equal to pull in the guest grab. One of the VM will run a single thread Unix bench. The other test case is both will disable the mwait intercept, and one of them will run single thread Unix bench. We can observe the performance improvement for disable mwait vmexits. Let's see why. In next slides, we can observe for the top command, both idle is equal to pull and disable mwait will cause the top command to show 100% CPU occupation. But when I use power top tool, for the idle is equal to pull in guest, we can see almost all the logical CPUs enter the C0. But for disable mwait vmexits, just the thread which run the Unix bench are in C0. For the core scope C state, we can see most of the time they are in C3 or C7. Yeah, they are in deeper C state, which means the single Unix bench thread can get a turbo boost. That's all. Any question? These patches are all merged to upstream, so you can have a try if you are interested in. Oh, David?
Oh, hi. Yeah, I worked a little bit on the QEMU side of the way to hold things. I would just, it's great work. I would appreciate it if you could share maybe the scripts that you use to evaluate the efficiency of that. Because while I did upstream it and it works functionally, I don't really know yet how to test how good they are and how well does all this work.
Okay.
So. Okay. If we could maybe post it on list, maybe we could put it somewhere in the contrib and QEMU.
Okay.
That would be great.
Okay.
Thank you.
Hey, for the Paravirtual TLB Shootdown, can you explain again what the preempted vCPU flag is used to do?
Which one? There are 2 flags here.
Yeah, can you explain how the guest uses that KVM vCPU preempted flag? What decision does it make based on that?
Because we need to know in the guest whether or not the initiators, the IPI initiator CPU need to know whether or not the target CPU is preempted or not. So itself it can know, but the host can know whether or not a vCPU is preempted. The preemption notifier on the host will notify the vCPU is preempted and be scheduled out. This time, the vCPU preempted flag will be marked, and before this vCPU next VM entry, the flag will be clear. So in the guest, another vCPU in the guest we can know this is this memory is shared between the guest and host. So in the guest, we can know whether or not the target vCPU is active or not.
Okay, a quick follow-up. Is there a race if the guest sees that a vCPU is preempted and then it gets scheduled in right after that?
It's all post blocks.
Okay. Thank you.
This is my third microphone today with no batteries. Cool stuff. I have a question about the guest support. So obviously, Linux guests support PV MMU ops because you upstreamed it. Have you engaged Microsoft?
Yeah,
Windows support?
then I observe the Hyper-V also has a similar feature, but the implementation is different. They use a hypercall then to call the vmexits instead of my a little different.
Do you have any plans to implement that, the Hyper-V enlightenment? Great.
Yeah, I remember Vatley implements that.
My question would be how this vCPU preempted flag is going to work in nested environments, because when you're running in L2, your L1 doesn't really know if his vCPU is preempted or not. Can we make it work? So we actually know in L2 if this vCPU is running or not.
In a nested environment?
Yes, because, I mean, from L2 you're observing this flag, and it tells you that vCPU is, for example, not preempted, right? But this information comes from L1.
Okay.
And it may not be true, right?
I will check it later and email you.
Yeah, for the toggle mode, I remember that the KVM strategies don't support the toggle mode to guest, because there's
Support what?
toggle mode. Your last topic, toggle mode.
This mwait?
Yeah.
Yeah.
Yeah. You mean that in this way, the other CPUs in the same package can get turbo boost on demand.
Yeah.
But the precondition of turbo boost is that you assign all the CPUs of a coordination, the hardware coordination to one VMs, right?
Assign what?
Yeah. The precondition of turbo boost is that in a hardware coordination, there's several processors.
Yeah.
And other processors satisfy some workload condition and temperature condition. Then the solid CPUs can boost.
Yeah.
So do you have the precondition that you assign all the CPUs of a hardware coordination to same VMs?
Do you mean run multi-thread benchmark instead?
I mean, if you want to turbo boost a CPUs of a VM, do you have the precondition that all the hardware coordination CPUs also assigned to this same guest? Yeah. Because if the different CPUs in one hardware coordination belong to different VMs, you may get the wrong information, I think.
Okay.
AWS has an instance with a huge build size with a lot of CPUs belong to one VMs.
So I'm not sure I understood his comment, but I think maybe the part that was not clear is that the first two optimizations that he mentioned were for overcommit, and this one is not. This one is not when you're overcommitting. This one is only to improve the latency when you can do like one-to-one, basically. When you use your host only to partition it across VM. Is that right, Wanpeng?
Yeah, I think even if there is no overcommitment of CPUs, you still need to satisfy that we have to assign all the CPUs of one. Yeah. The precondition is that I think we should assign all the CPUs of one hardware consolidation to one VMs.
Yes, either
the
that
only
or
instance,
the other VM is not doing.
yeah, the only instance I noticed that is Amazon's C5, the new instance, and only when the C5 is a big C5, that means we can assign all the physical processors to one VMs can enable this feature. Yeah.
Okay, thank you.